Welcome back. In the last lecture, I talked about Harold Markowitz's work on mean variance portfolio theory. Then we progressed on to William Sharpe's CAPM model. Together with the Black-Scholes model that we shall be talking about later on when we talk about option pricing, these three form the cornerstones of contemporary finance. We shall start today by a brief recap about what we did last time, and then move on to the William Sharpe's model, further discussions on that, and then to index futures and how the theory of Sharpe and Markowitz becomes relevant to index futures. So, we started in the portfolio optimization by considering two risky assets, and we found that we have three equations and two unknowns, the composition vector of the two risky assets x 1 and x 2, and therefore, the two can be eliminated, and when we and thereby we get a curve in risk return space, the risk along the x axis and return along the y axis, that is the usual practice. The portfolio possibilities curves turns out to be a hyperbola. Now, here I would like to emphasize that we are concerned with the section of the hyperbola that is in the right half plane, because x, which represents standard deviation, cannot be negative. The other fallouts are that those combinations only that lie on this curve are feasible, and corresponding to every point on this curve, we have a unique combination of the two securities 1 and 2, which are both risky assets, and the portfolio is fully determined by the composition of these two risky assets x 1 and x 2. I repeat, only combinations that lie, risk return combinations that lie along this curve are feasible. Number 2, each point corresponds to a unique composition vector, and number 3, the portfolio is completely determined by the composition vector. Then we consider the case of a risky asset and a risk free asset, and we found that we get a straight line as the a pair of straight lines, in fact, as the portfolio possibilities curve, and the efficient frontier is obviously the straight line AF. The straight line BF is dominated by AF, therefore, all investors would like to invest along AF rather than BF. The two risky assets plus the risk free asset is really the prototype model of the n securities or the practical version of the mean variance portfolio optimization theory. In the two securities case, as you can see here, we have two securities A and B, and the section of the hyperbola that passes through A and B constitute the portfolio possibilities curve comprising of these two securities alone. But when we add the risk free asset to this combination, we can achieve any point within this triangle represented by P, F and Q. And any point here would be any point here, for example, would be a combination of risk free borrowing plus a point, let us say this point, together with risk free borrowings, and therefore, we can achieve any point within this section. Now, the important point is, as you can see, this is what portfolios are possible, this is the feasible region. Whatever portfolios are possible will lie somewhere within this region. What portfolios are actually efficient, what portfolios would be superior to the other portfolios is given by the tangent, which is the straight line F P. The tangent to the hyperbola at the point P gives you the efficient frontier, that is the set of portfolios which are efficient, which are superior to all other portfolios, as can be easily seen. Any other portfolio lying below will have a corresponding portfolio lying on F P produced if required, which will have a superior return for the same level of risk, or the other way around, it will have a lower risk for the same level of return. So, obviously, all portfolios which the investor would be interested in would be along the tangent Fp. And how do we get this tangent? As we discussed last time, the tangent is obtained by maximizing theta. Maximizing theta tantamounts to maximizing tan theta in the first quadrant, and therefore, we have maximization of tan theta as the objective function, which is nothing but R p minus R f divided by sigma p. Then we discuss the 3 securities case. In the 3 securities case, it is a slightly complex scenario, corresponding to everywhere. If we select the 3 axes x, y and z to represent the standard deviation, the expected return and the composition of the third security, let us call it C, or x 3 is the composition of C. So, for every point along the z axis ranging from minus infinity to infinity, the negative values of x 3 obviously represents short selling of C. So, any point you select along the z axis have a plane which is parallel to the xy plane, and you get a hyperbola. Therefore, the entire, now we do not have a feasible curve, we have a feasible surface in this case. The feasible surface consists of an infinite family of hyperbolas, with each family corresponding to a point along the z axis, from where we get a plane parallel to the xy plane, and on that plane we have a hyperbola as the feasible region. So, our optimization question or optimization problem now becomes a 2-step procedure. We first identify that hyperbola such that the tangent from the risk free line to that particular hyperbola has the maximum slope, and then we work out the coordinates of the point of contact of that tangent with that particular hyperbola, which will give us the composition of the composition vector of the portfolio, which will solve the portfolio optimization problem. This was where Markowitz took us. The important things were that expected return was determined as a function of risk, and number 2, risk was measured by standard deviation. These were 2 cardinal features of the mean variance portfolio optimization framework as propounded by Markowitz. Now, William Sharpe came along, and William Sharpe said, okay, let us assume that all investors in the market do the Markowitz optimization. If they do so, then what would be the respective pricing of various securities in the market? You see, a market will have a certain supply of each security, and at equilibrium the supply of that security must equal to the demand for the security. The demand for the security in turn will be created by investors vying with each other to buy the securities, which will create a price. So, the question that Sharpe wanted to address was, how does the price react to the market forces, or what risk does translate into an expected return as represented or as played by the market participants. So, that was the question that he wanted to address. He made the assumption that all inputs into the optimization problem are homogeneous, that is, they are the same for all investors. All investors use the same framework for optimization, which is the Markowitz framework, and keeping these 2 assumptions and assuming the necessary fact that supply must equal to demand for each security, what are the implications for the pricing of securities in the market? That was the question he addressed, and he came up with the CAPM. Now, when we optimize the Sharpe ratio, when we maximize the Sharpe ratio, keeping in view the Markowitz conditions, we found that we can add a security to an existing portfolio so long as this particular condition holds. RS is the security that is to be added, RS minus RF is greater than beta S into RP minus RF. So long as this condition holds, you can improve the performance of your portfolio by adding security S to your portfolio P. and if the negative holds, if it is if the less than inequality holds, you can short S and thereby increase the performance of your portfolio P. So, the contention was, because in both situations we can improve the Sharpe ratio by adding securities at equilibrium. Since this cannot be done in an equilibrium scenario, we must have in equilibrium R s minus R f is equal to beta s into R p minus R f. Then it was argued that on the premise of the various assumptions of the CAPM model, the portfolio P which an investor holds, because all investors are having the same inputs and are adopting the same optimization framework, therefore, all investors would be invested in a portfolio having the same proportion of assets. Of course, the actual portfolio will comprise of this particular portfolio, which will comprise of the same proportion of assets plus a certain proportion of risk free assets, which will depend on the risk tolerance of the investor. But this portfolio, the risky portfolio, let us call it P. The risky portfolio P, which comprises of the set of risky securities that all investors are having, under the CAPM assumptions, this portfolio is identical for all the investors, and that being the case, the market outstandings for each of the securities comprised in portfolio P must also be the same as explained last time. And that being the case, this portfolio P would represent or would be the same as portfolio M in terms of security proportions, and therefore, we can replace P by M in the optimality condition, which is R s minus R f is equal to beta s into, now it becomes R p becomes R m minus R f, which is the statement of the CAPM model. So, now that is all these things, please note, all these things are on expected value basis, all returns are expected returns. As we have been emphasizing, we are talking in the case of CAPM in an expected return risk framework, risk expected return 2-dimensional framework, and therefore, the CAPM model relates expected return to the beta of the security, expected return of a security to the beta of a security. The actual return, of course, can vary around that expected return, as we have in a regression equation with a certain random component, which is represented by this expression E I. The spontaneous return will not invariably fit into the CAPM equation, will have a random component, which is represented by E I. So, the key takeaways are of the CAPM model: the total risk of a stock portfolio can be segregated into two orthogonal components. Number 1, the systematic risk, which is the beta risk, which is captured by the sensitivity of the return of the expected return of the portfolio or the security to the market returns, which is captured by beta, which is the systematic risk, and a random component, which is represented by E I. And the two important fallouts are: market does not price total risk. As you can see from the CAPM equation, from this particular equation, the expected return on a security is related to its beta, it is not related to its standard deviation. That is a very, very important outcome of the CAPM model. Market does not price total risk, market prices only systematic risk. Only the systematic risk component of the market is converted to a price, and expected returns are in tandem, move in tandem to the systematic risk, with the sensitivity represented by the beta of the security. Another important fallout is that the unsystematic risk must necessarily be random. Why is that? If there was a pattern embedded in the unsystematic risk, for example, if E I had a certain pattern, the market would decipher that pattern, and once the market is able to decipher the pattern embedded in E I, the price would capture that pattern, the price would reflect that pattern. That is what we call efficient markets, in fact. So, this EI would, if it had a pattern, it would be captured by the price, and therefore, the EI would no longer be remain unsystematic risk, because then market would be pricing this component of risk. Therefore, by its very definition, EI has to be a purely random component in the CAPM model. Now, let us consider certain examples. There are certain examples which are contained in the subsequent slides. I will talk about the outcomes of these examples in a summary which is given later on. These slides are available together with the lecture. So, viewers can have access to this, but this is the summary of what is contained in this slide. We have a market portfolio. The market portfolio has a total risk of 4%. The systematic risk is also 4%. Obviously, being the market portfolio, it has no unsystematic risk. This is 0, and the expected return we are projecting as 12%. So, I repeat, total risk, that is sigma m is 4%, systematic risk is also 4%, beta is obviously 1 for the market, unsystematic risk is 0, and expected return is 12%. Now, we have a portfolio P, which has a total risk of 6%, that is sigma p is equal to 6%. We have a systematic risk of 4% here, an unsystematic risk of 4.47%, and a expected return of 12%. This is a hypothetical portfolio that we have constructed, where the total risk comprises of both systematic risk and unsystematic risk. Both the risks are incorporated or are part of the total risk of portfolio P. Portfolio Q and S, if you look at it carefully, portfolio Q has a total risk of 6%, a systematic risk of 6%, therefore, the unsystematic risk is 0, and its expected return is 16.5%. Now, the interesting feature is, despite having the total risk as portfolio P, the portfolio Q is able to generate a higher expected return. And why is that? Because the entire risk has now been transferred. What is the difference between portfolio P and Q? The difference between portfolio P and Q, if you look carefully, is that portfolio P has both systematic and unsystematic risk. Portfolio Q has only systematic risk. Therefore, the unsystematic risk component of portfolio P has been transferred to the systematic risk of Q. In other words, this unsystematic risk which was unrewarded by the market, and when a same level of risk, total risk, that is, same level of total risk is taken by an investor, but he diversifies in such a way. Now, this is important. He diversifies in such a way that the entire unsystematic risk is taken out of the portfolio. He does excellent diversification, and he eliminates all unsystematic risk. Then he ends up with a position where he has a superior expected return, where his portfolio is likely to perform better than a portfolio which has a certain component of unsystematic risk. In other words, coming back to it, unsystematic risk is not contributing to the generation of expected returns under the CAPM assumptions. A parallel portfolio S, again it has the same systematic risk as P. It has the same systematic risk as P, and its total risk is entirely systematic risk. Now, if you look at this P and S, they have the same expected return of 12%. P and S have a same expected return of 12%, but you look at their total risk. P has a total risk of 6%, S has a total risk of 4%, and therefore, we are able to generate an equivalent expected return or effective return by a portfolio which is having a lower total risk. Why? Because this unsystematic risk is the taking of this unsystematic risk is not translating to expected returns. That is the important part. Therefore, the outcome of this and this comparative evaluation is that the expected return of a portfolio can be improved by eliminating or reducing unsystematic risk, because market does not bother about unsystematic risk. It does not reward an investor for taking unsystematic risk. It believes that the investors are good enough or competent enough to do adequate diversification to eliminate all unsystematic risk in their portfolios, and therefore, only the systematic risk component is captured by expected returns provided by the market. Now, whatever I have been talking about, let us translate this into some quantitative arguments. You can see on this slide here, sigma p square, that is the variance of a portfolio, is represented in terms of the variance, the sum of the variance of the securities themselves, which is the first term, and the sum of the covariances, that is the variances between securities inter se. A with A's covariance with B, A's covariance with C, and so on, B's covariance with C, and so on. And the first term is the intrinsic variance of the securities alone. Let us now look at a portfolio. Let us now look at a portfolio which is equally weighted in all the constituent securities. We have a total of n securities. Let us say we have one rupee to or one money unit to invest. So, the amount that is invested in each of the securities is 1 upon capital N, number of securities, and therefore, putting xi equal to 1 upon n, we get this expression. This expression can be written, you take 1 upon n outside the purpose of this will be seen soon in the next step. In fact, for the moment I take 1 upon n outside the sigma and I write sigma I square upon n, and similarly I multiply and divide by n minus 1, keep one of the n's outside the summation and the other n inside the summation, multiplying dividing by n into n minus 1. Now, looking at the first term, this expression, if you look at it carefully, is the aggregate of all the variances of the securities divided by the number of securities. So, in some sense it is the average variance of the securities. Let us now come to the second term. In the second term, what do we have? We have the covariances between various securities. Now, security 1 will have a covariance with security 2, security 1 will have a covariance with security 3, and similarly there are n securities. So, security 1 will have a covariance with n minus 1 other securities. Remember, the covariance of security 1 with security 1 is nothing but the variance of security 1 which is captured by the first term. So, that will not be a part of the second term. The security 1 has n minus 1 covariances with the n minus 1 securities. Similarly, security 2 has n minus 1 covariances with all the securities 1, 3, 4, 5 and so on. Similarly, security 3. So, we end up with a total of n into n minus 1 covariances. Of course, please note that sigma of ij is equal to sigma ji. Therefore, the distinct covariances will be n into n minus 1 divided by 2, but we are not concerned with that. The total number of covariances will be n into n minus 1. There will be pairs of similar covariances, but the total number will be n into n minus 1. So, what I am trying to say now is that we are having a summation across all the covariances and we are dividing it by the number of covariances. So, this term again is in some sense average covariance between any pair of securities. To repeat, the first term is 1 upon n into the average variance across the n securities, and the second term is n into n minus 1 into average covariance among pairs of securities. Now, in the limit that n tends to infinity, the first term gives you 0 and the second term, if you look here, n upon n will give me sigma bar j k, and the second 1 upon n sigma bar j k will give me 0. So, the second term does not give me 0, the first term of course gives me 0, and the net outcome is this expression. So, what have we tried to establish by this analysis? We have tried to establish 3 things. Number 1, there is some part of the total risk that tends to 0 as the number of securities tends to infinity. In other words, as you diversify more and more, the risk tends to decrease, the total risk tends to decrease, because one of the components of the risk tends to 0. Number 2, that part of risk which approaches 0 as the diversification increases is dependent upon the intrinsic variances of the securities. Dependent, you see, if you can clearly see that this term comes from here, and this term is nothing but the intrinsic variances of various securities. There it has nothing to do with the relationship among securities. So, the part that tends to 0 is arising out of the intrinsic variances, and the third conclusion that we get is that the part which is not tending to 0, in fact, one more conclusion is that the total risk can never be made 0, and the part that is not tending to 0 or that remains finite, non-zero, that remains non-zero, it arises out of the covariances between pairs of securities. So, 3 outcomes which are very important. Number 1, some part of the total risk can be eliminated by diversification, you increase the number of securities. That part which can be eliminated by diversification is related to the intrinsic variances. The total risk cannot be made 0, and the total risk cannot be made 0, and the part that cannot be made 0 arises due to inter se relationships between the various securities. This is of course, this makes the assumptions which are embedded in that we are making equal investments in the various securities and n is tending to infinity, but the message is clear. The message is diversification reduces risk, diversification does not necessarily make the total risk 0. I repeat, that diversification does not necessarily make total risk 0, and number 3, the component which is tending to 0 is arises due to the intrinsic variances, and the component that does not tend to 0 arises out of relationships among securities, and this part which tends to 0 is given the name unsystematic risk or diversifiable risk, and the part that does not tend to 0 is called the systematic risk or the non-diversifiable risk. Now, based on the assumptions that we had in the CAPM model, the regression assumptions that the market return and the random term are not correlated, we have the outcome that the risk can be partitioned into 2 orthogonal components, which we saw in the previous slide also. This reiterates that we have 2 components of risk, one component of risk which is related to the regressor and the other component of risk which is random. The analysis is here. It's quite straightforward, and what we end up with is that the total risk of a security, is equal to this component which is the systematic risk, the beta risk. Beta appears in this first component. This is the beta risk of the component of this of the total risk, which is the systematic risk related to the sensitivity of the return to the market return, and the random risk, which as I said can be diversified away through appropriate diversification, can be eliminated, can be reduced through appropriate diversification, which is termed as unsystematic risk. So, as I mentioned, to reiterate, the unsystematic risk must necessarily be random and uncorrelated with systematic risk, because if there were any pattern in that pattern would be deciphered by the market participant, built into the price, and then it does not continue to be unsystematic risk. Now, when I started this topic, I gave you an example. If you recall, there were 2 securities there, security A and security B, both had a return of 10%, expected return of 10%, and both had a standard deviation of 6%. And when we come and they had a correlation coefficient of 0.50. And when we combine these securities to form a portfolio with equal weightages, we found that the weight of the risk of the portfolio turned out to be 5.20%, whereas because the returns of the two securities are 10%, because the returns of the securities are 10%, both of them, any linear combination of them must have a return of 10%, and which is what happened. In other words, to repeat, you have two securities A and B, both having returns of 10%, both having risk of 6%, but when you are combining them to form a portfolio, you are having a return of 10% with a risk of 5.2%. Obviously, these three things A, B and P, the portfolio cannot remain in equilibrium if standard deviation is to constitute the measure of risk. Here we have an anomaly. To explain the anomaly, we will come back after the break. Thank you.